Hi everyone, welcome to TAG. Today we will be looking at a program in assembly. So here I have a terminal, and then I have a program called shell. Ooh, okay. So here, wait, it's let's see. Sorry, I think the streaming might not work perfectly. Oh well, screw that. If it doesn't work, we'll record it as well. But anyways, so here I have a shell, and then I have a program called shell. So if I run it, it'll give me this prompt, and then it'll ask me what is the password. So I don't know the password, so I'm just gonna type in some letter, something, and then it's gonna load, saying please wait while we process your password, and it says access denied. So it looks like we cannot access this shell. But what if I told you the password is just simply the password? It's a very secure password. And we wait. We get access granted, but too bad we don't get shell. Shell has been disabled. So is maybe there's a way to get shell. So today we will be looking at what this program actually does from an assembly point of view. So for the optimal thing, I'll ask every one of you to please uh, open up your browsers if you have one, or if you have a laptop, open up and then type in our website tagudd.github.io, and then you'll see our post that's overflow with characters files. So we have a program here, and that will download you a binary. You click on it, you get the shell program. Although it might not run on your machine if you're not running a Linux, that's okay, because we have this thing. We have an SSH. So if you're on the Linux or Mac, you can use SSH, and we can SSH into this. Or if you don't have any of those, if you're on Windows, you can download some tools. I think like some terminal tools to do SSH. But I get if you want to do that and follow along, that's cool. If you don't have the time or don't want to do that, that's also cool. You can just watch. But the first part will actually everyone can do. So first of all, I would like you to, once you download the program, we want to install something called IDA. So IDA is this really cool. Not that. IDA is a very cool disassembler that allows you to look at all the code that's inside a program. So if I open this, I want the free version. Let's see if I could find it. Okay, this one. So here we have the download demo version, and we have the IDA 7.0 freeware. So if I zoom in on that, we have this thing. We want to click on this one. So this will take you to this download page, and then you have one for Windows, Linux, and Mac. So you don't have an excuse for not having this be able to run. So then once you download it, you basically run it to install, and that would get you to the IDA. So when you open up IDA, I'm just going to go open up another instance of IDA, and let me close that one. So here, okay, let me close that as well. So once you install IDA, if anyone wants to install IDA, is anyone going to install IDA? Raise your hand so I know to wait for you. Okay. Is it anyone else? Okay? Rebel, you want to install IDA, or you want to just follow along? It's fine either way. Okay. So once you install it, please look up so I know that you're done. Okay. You're good. Are you good? Okay. Are you good? Okay, you are installed. So when you open up IDA, you'll get a screen that says IDA, and then it'll let you open up. So to disassemble, you want to click on New. It'll let you browse for the file. But since I already have it, I can just actually go over here and load this shell. So here we have some cool graphs. So I think last week last week on showed us also how kind of this IDA thing. We're going to use this IDA tool to actually disassemble this program. So wait, let's see if I have a mouse. That might be a problem. Oh. So in this one, we'll run, if you're running on any Windows or Mac or Linux, this will all run correctly. So we look at this. On this graph, let me zoom in. Does anyone have like a mouse I can borrow? That might be a problem if I have to navigate using the trackpad. Okay, let's see. Okay. Yeah, thank you. Okay, yeah. So here, let's look at, so we look at the sidebar. We see a lot of functions. And a lot of those functions are in purple or pink, and some of those are white. So a lot of these functions you see here are basically either functions from other methods or other programs, or there are functions that are just in every Linux binary. So let's look at this. So we have some methods called like puts, setbuff, strcmp, and we have all these different functions. So all of these functions you can see here are all part of the standard C library. So if you run any C program, this DLL or shared library, as it's called, this program will actually be loaded with your binary program, and you will be able to call those functions in that C library. So these are actually pink, and you notice that actually over here it says it doesn't give you actual code for this. You notice how this says extern, which means it's external. Something external, which is not on this whatever, it's not on this binary. So we don't care about those. So let's look at our main function. So we see there's like some code, a lot of assembly code, and then we have another function called auth, which has some more code. And then the third function, I think, is read input, and we have some more functions. Right. So which one do we want to look at first? What do we want to choose? Huh? Oh, main. Okay, we can try with main. So this one is very straightforward. You don't see any arrows, so that means there's no if statements or loops or any of that jazz. So let's zoom in. We see that we start with the push RVP and move RVP RSP. Does anyone know what that is? It's okay if you don't remember. Does anyone want to give a guess what those do?
Previous frame pointer and then the current stack pointer.
Oh yeah, yeah. So it does some stack stuff. We don't really care about it. So then we see that it calls a function get egid. So this is a Linux function. If you don't know what it is, it's fine. It doesn't really matter. It's something that's just there. So does anyone happen to know what it is? It's fine. Oh, you?
It should be something related to shell permissions.
Okay, shell permissions.
If you grab yourself a shell, it's a courtesy function frequently used in C.
Okay. Oh yeah. So what we see here is, yeah, we have something shell permissions. So we have a get egid, and that gets returned into EAX. We move into register EDI, and then we call set GID. Who remembers what the functions, how functions are called in Linux or Mac? Like which registers do we use for calling a function?
Parameters?
Yeah, parameters.
Yeah, I was gonna ask you. I forgot what those were. The EDI.
Yeah. So again, we can, if we forget something, it's always somewhere. So of course, I think I kind of forget it sometimes. So we can always go back here and look at it. So we can scroll down. And okay, so we have here, we are on system V, which is some ancient name for anything Linux. This one right here, we're system V, and we see Linux is over here. We see the order of registers is RDI, RSI. Let's see if I can zoom in. No, I can't. Okay. So we start with RDI, RSI, RDX, RCX, R8, R9, and then XMM 0 through 7. So what we have here is we're passing into the first argument of passing in an argument into EDI, and we're calling set GID. So that's, again, is a courtesy function in lots of CTF stuff. Then we have a set buff. That one, we see the second argument is in 0. We're passing 0 for the second argument, and RDI is the first argument. We're passing in RAX. And we see that that's like the stream. So not important. All this is like preparation code, so we don't really care about that. Now we go down into puts. Ooh, we get an offset and then this thing. And then we call puts. Does anyone know what puts does? Oh yeah, we print out the string. So what are we printing out here? Does someone recognize this? So we're calling puts like 1, 2, 3, 4, 5 times. What are we printing out? First thing you see?
When you run shells.
Oh yeah. So it's basically that prompt, that splash screen that I get. So if you notice that these are offsets, if you double click on them, we see that is actually, and I don't think I can zoom in on that. Sorry. If I double click on that, we see that it's actually a string in memory. And remember that DB instruction? The DB that defines like memory. So then you can input a string into some data. So here we actually see the use of DB. And then we have a null terminator. So then this is a string right here. And that's what we see that we're printing out. So we're moving on. There's nothing much in main. And then we have the next thing is called auth. So do we want to look into auth now? Okay. So let's look into auth. And we have more code. Oh, we got arrows here. So the cool thing about IDA is it lets you visualize all the if statements and the for loops and all the loops. So basically, you don't have to go and manually look at where the loops start and end. It's all here. So let's look at the first loop. So we know that this is a loop because we see this blue arrow pointing from the end to all the way up to the front of back in code. So that's a loop right there that we are going past, going over and over again. So let's start from the beginning. We have a printf. Again, we're passing into our EDI, and we're saying, please enter a password, please. And then we call this function called read input. What are the parameters we're passing in? It's interesting. Does anyone know what we're actually passing into read input? So let's look at, give you a few more minutes to think about it. Okay, so we notice we have this Lee instruction. Does anyone remember what a lead instruction does? Huh?
Load effective address.
Oh yeah, that's what it stands for. But do you want to explain more?
So load the address, the value of RBP plus whatever S1 is, which is 30x.
Okay.
So load that memory address. So
Yeah.
RBP minus 30x.
So yeah, something like that. So we see S1 is actually corresponding to this thing, S1 minus 30. So we see that it's an offset into something, into RBP. So we're gonna let that sit for a while. We're gonna look at the other part of the code. So now we go into printf. We have the please wait, and then it passes that into printf, and then we continue. We have a var4, and that's just an offset again. So we have some sort of variable, but we don't know what it does. So now we have a loop. So we compare this with 4. And then if this is less than or equal, we jump over here. Do 1, go into EDI, so we're passing an argument again. And then we're calling sleep. And then we're passing 2e into put char. And then 2e is actually just a dot in ASCII. So actually, what you saw me do there is actually I told IDA that I know that this is not a hex value. So it's actually like a character. So you can actually modify what you think this is if IDA's predictions are wrong. So you can actually, the other cool thing with IDA is it's not just a static disassembler. You're able to make your code a little bit more readable, so that way you can actually disassemble a little bit faster. So you don't have to annotate everything. So here we have a var4, we add 1 to it, and then we go back to the beginning.
How are you able to, what's like the way to edit it?
Okay, so right click. So right click on something, it gives you options on how to modify that. So this one's like you see here is plus var4, but if you actually modify it to like whatever it was originally, this is what you would actually see like in a disassembler that doesn't know anything about it. So this is what a dumb disassembler would say. You have RBP minus 4, and you might have seen this notation a little bit familiar, but we actually know that this is a variable, so we actually turn that back into this. So IDA is actually a little bit smarter. It'll actually tell you that this is probably a variable. So from looking at this, does anyone know what maybe var4 is doing? Or what's the purpose of var4? Okay, a counter for a loop. So we notice that this is a loop, right? Because the blue arrow going back. And we know that this is a counter because this one's incrementing it 1 each time we go through the loop, and this one's comparing if it's less than or equal to 4. So we can actually change this. So I'm pressing N right here. You can also go right click on it, and then you click on the rename button, and then there's an N shortcut key to it. So here you can actually change it. So I don't like var4. It's very meaningless. I call it CTR or counter. So that way, I actually know what this variable is from a glance. So now the next question is, which block do we jump to after we're done with this loop? Like where do we exit to? To the right? What's the first instruction? Just read out the first instruction on the block. Okay, so now we notice that once we're done, we see that this red arrow is actually taken. So there's a green arrow. That means that the successful jump, and the red arrow tells us that we did not jump. So we move into this block. So now we call puts again. We do a new line for some reason. And then we do something interesting. So again, what are we doing here? We're doing a str compare. Does anyone or str cmp? Does anyone know what that is? String compare. Yeah. So we're comparing two strings. So what two strings are we comparing? Okay, so we're comparing something. So we have this comparison S2. We can actually rename this. I like to rename it, or rename it somewhere. Let's call it pass, correct pass. So that one tells us that this is the correct password. And then we're doing this one. We're doing load effective address, RAX, S1 into RAX, and then move it into RDI. So this one is actually not S1. I feel like that's kind of not very descriptive name. Let's name it input or user input. So here again, I can do a rename. You can click on that. It'll give you the screen and you can rename stuff. It's much easier to make your code a lot more readable. So we have a string compare. And then we have a test EAX. Why do we have a test EAX? Does anyone want to know? Does anyone have an idea why we have this instruction? And then we have this one under it. What are we doing in these two instructions? Okay, yeah, we're testing if it's 0. So J and Z means if it's not 0. So let's zoom out a little bit. It's kind of difficult to see. So let's go if it's not 0. J and Z, we jump over to this location because this is a green arrow. And that means we jump somewhere. And then we go into here. We see move EDI and this string, access denied. So I guess this one is telling us that your password is wrong, try again, access denied. And that's if it's non-zero. And then right here, if we go on the other side, we see that we have a move EDI and inputs, access granted. But then we do something interesting. We have another jump. So what are we doing here? These 3 lines after the puts, access granted. Okay, check if it's null. But if it's null, what is it also? Like, what numeric value? 0. Okay. So we're testing this if it is 0. So we see that if JZ, if it's 0, we jump over here. We say, sorry, shell access has been disabled. And then it exits. And then you have this thing. If it's non-zero, it says you get a shell. So here it looks like if we can just set the debug flag or this debug variable to anything that's not 0, we get a shell. But unfortunately, our debug flag, if we click on that, is actually set over here to 0. This one's a question mark, but it's actually 0. So we see here, our hopes of getting a shell are non-existent. It's impossible. So you double click on it. So you see this yellow highlight on this debug character. So now you double click. It'll actually take you to this another list view, and you see that debug is defined over here. You see a question mark right here, but in fact debug is the value 0. So I guess we can't get a shell. Huh? Oh. What did you get? Oh yeah. That's we look.
But where does it hit zero?
Oh, it's a question mark.
The question mark means zero?
Yeah. So question mark in essence just means zero. Oh. I forgot to turn off redshift. That looks kind of yellowish to you, right? Yeah, that's because I have like a blue light filter. I forgot to turn it off. Okay, there you go. And if it looks yellowish from now on, just someone holler at me and I will turn it off. Because it also gets recorded as that yellow tint. And people on looking at their screen on YouTube will not like that. Because it's kind of yellow. So, yeah. Just let me know next time. So now, we notice that we don't get to have a shell. I guess we're just gonna go home and think about the times when we are able to get a shell. Not today, not today. But wait, we haven't looked at one function. We have a read input. So let's double click on that. We get this thing. So now we have another loop, as we see here. So this one's a little bit more interesting. So remember, we passed in a variable. We passed in something into RDI, user input, the address of the user input variable into RDI, and that RDI, if we double click on it, corresponds to this RDI. So we notice this is actually how we're calling methods and how we're receiving parameters. So we move RDI into this var 18, and we're removing the address of it into var 18. So not the actual variable. So you gotta remember that. Is it an address of a variable or is it the variable itself? Because you can get very wrong if you think about it, if you screw that up. So here, we'll just call it user input address. And again, we can right click on it and it will let you rename it. Or you can press the N shortcut key, which is very nice. So that way I don't have to click on it. So here we go on to the next line. It jumps over here. We call get char. Okay. Anyone want to? Does anyone know what get char does? Okay, gets a character. So, actually, let me show you another functionality of IDA. I feel like I'm kind of advertising it, but it's a very good disassembler, and it's free. But yeah, I'm just shamelessly advertising it. So another functionality is if you want to add comments. So you see the semicolon key on your keyboard. You can click on it. You get this thing. You get this text. You get this text box. You can enter comments in here. And let's say blah. I enter, or I have to click OK. It will give me a comment right here that says blah. So I can also re-edit it. So I just press semicolon again. I can say this function gets a character from user input. So something like that. So now you see like a nice comment. So it's very useful if you're documenting stuff and you don't remember what this thing does. So now we go down. We have var4. So we don't know what var4 does. Actually, does anyone? So now we have var4. We move EAX into var4. What are we doing with that?
It's another loop counter.
Is it?
Where the character?
What's in EAX right now? We just called get char. Okay, it's a character. So we realize that this one is moving this into a temporary variable. So let's just call it char for now. So it's just a character. we're comparing it to whether if it's equal to whatever what we're comparing it with 0x f f f f f f f f, and we can actually convert this into more useless stuff. But basically, it's also -1 in signed integer. So why are we comparing it with -1? Does anyone know what's special with -1 in the get char? Well, if we don't know, we can always, for lots of functions, let's do some. We can do something called a man page. So does anyone know what a man page is? So this is only Linux. Sorry, if you're using a Windows, I would just Google it. But man pages are cool in Linux if you're using that. So we can actually, if we don't know a function, we can just do man get char. So then we're just typing the man, and then we're typing in like, oh, I want to get what I want to know what get char does. So we show this man page, we see a lot of functions, and then we see get char right here. So we see that get char is equivalent to this thing, this function. If you pass an std in, and then get c is equivalent to f get c, and then blah blah blah. Okay, f get c reads in the next character from stream and returns it as an unsigned char. I don't know what that is. Cast for an int or EOF or on end of file or error. So here we see that f get c or get char all return like a character that the user input. But it also returns an EOF if we are at the end of the file or if we get an error. So what's the cool thing is if let's say we were reading from a file and we reach the end of the file, this value EOF gets returned instead of a valid character, so that we know that, hey, the file has been, we're done with the file, there's no more characters to be read, and maybe you should close it. So here, what we have here is we're comparing whether if it's an EOF flag. So EOF is actually -1 because there's no characters that are negative for obvious reasons. So here, we compare with -1. If this is not equal, so NZ, in some cases, NZ means not equal. Some cases, it means NZ is not 0. So it depends on what instruction you called before it. If it's a compare, it's not equal. If it's a test, it would be not 0. So yeah, it's a little bit interesting to remember, but yeah. So we continue. If this one's not 0, we actually jump to somewhere. We jump to this thing. So if it's not EOF, we jump over here. If it is EOF, we actually jump down here and we return. Okay, so we return on EOF. So interesting. And then we, if it's not 0, we compare with the char. We compare the char with hex 0a. So remember, these are characters. So we're probably comparing it with the character, not with the hexadecimal value a. So let's convert that into something. Well, IDA doesn't have that option. Let's see if I can do into edit. So let's see if I can find it. Okay, so here I went down into edit. I went to operand type, and then I click on character. This one obviously doesn't do anything. Okay, whatever. Come on, Ida. Okay, but anyway, this one, hex A, is actually the new line character. So it compares it with the new line, saying, is it a new line character? We do a jump, not equal. So if it is a new line character, we go into this branch. If it's not a new line character, we go here. I know it's a little bit confusing, especially with the jump not equal, it's kind of unintuitive, kind of the other way of thinking. But you just have to make sure. You got to make sure if it what's comparing and then if it's a jump z or jump nz. So here I'm just gonna add a comment. See char is a new line. So that way we don't have worries. So this one, char is not a new line. So here we first look at if it's a new line. So if it's a new line, we actually go down here. We go into this. We extract the address of the user input, and then we put a 0 into it. We tag a 0 there. That's a null terminator. Yeah.
The compare does if it's equal, it goes to 0, right? The flag. Is that right?
Huh? Yeah. If it's equal, the flag's set to 0.
Because it is like subtraction, right?
Yeah, it's subtraction. Yeah. So we actually can use this subtraction technique to test if two values are greater or equal, greater or less than or equal, and all the different comparisons, just using compare. So it's a very nice instruction. And then so here we see that we're moving 0 into the address. So this is like a reference, like we're setting something into memory. And the memory starts with that user input, that value. So now we're setting values. Earlier we were accessing addresses. Pointer. Yeah, pointer. So, and also we also want to note the byte here. So byte is 1 byte. It's a smallest addressable thing that we can do in assembly. So now we go into the, if it's not a new line, we go here, we move char into EAX. So that one character we read, we move into EDX, which I don't know why you would do that, but that's dumb assembly. And then we move user input adder into RAX. So now we're moving an address. And then the last instruction, we're actually moving that byte into RAX. So we're setting another memory set right here. So we're setting a value. So we notice that in both cases, we're setting the 0th element in that address. But what about if the user inputs multiple characters? How does that work? So we actually notice something interesting. We have we add 1 to the address. So why would we do that? Or what does that do? Wait, can you say it louder?
You shift like the next by 1 to.
Okay. Yeah, so we're shifting the entire pointer. So we're shifting to the next character in that user array, in that input array. So what we see here is we have an array. And then we're trying to fill that array with that user input. Right? Everyone get this? And then we're moving the pointer 1 by 1 until the user inputs a new line character. And that's when the parsing stops. So now let's go back. I know we kind of digressed a lot, but now we can go back here. And do we see a problem with that?
You only get 20, no, not 20, 32 bytes.
32 bytes. Okay. So we don't get a lot of bytes. So again, if you went to my CSG meeting, we noticed we explored something called a buffer overflow. So over here, we noticed that we don't have infinite amount of memory to store this user input. Where are we storing it, actually? That's another good question. Where are we storing it? We notice that this user input array is actually stored somewhere in relative to RBP. So few weeks ago, we were covering something about RBP. Does anyone remember what RBP does? Or what's the register for?
Base pointer.
Okay, base pointer.
Keeps track of the stack.
Yeah, it keeps track of the stack. So now we're going to go a little bit more detailed. So we have a base pointer, and we have a stack frame. This stack frame is basically where our function, all the data of our function lives. So basically all your local variables, all your buffers. So in this case, the user input array variable, that's where everything lives. But what else lives on it is the return address. So now let's actually look a little more detailed on what this auth function does. So first, we push the old value of RBP, so the old base pointer of the parent function. And then we move RSP, which is a stack pointer, into RBP. So this becomes our new base. So this allows us, so in the reverse, we'd actually move RBP into RSP to pop that stack and then pop the old RBP. And now we have a new stack. We have the old stack frame, and then we return to the parent function. So we scroll down. Indeed, we see that same thing. Of course, the leave instruction is very interesting because it covers two instructions in x86. A move RSP into RBP, and then we have a pop RBP, and then we have a ret, and then the return statement, or ret n. So this is kind of interesting. So we have some stack here. So we have a. So now we want to talk about the push instruction. What does it do?
Track 4 bytes from the stack.
Okay.
Put the variable stack.
Okay. Yeah. So in a 32-bit, of course, in a 32-bit, we would actually subtract 4 because 4 bytes are in a 32-bit integer. But we're on a 64-bit machine, so it's 8 bytes. But you're close. So in this case, when we're pushing RBP, we're actually subtracting RSP, or the processor is actually subtracting RSP in the background and then moving that variable into that slot. And then when we return, we're we're first extracting that value that we have on the stack, and then we're incrementing the stack pointer. We're adding it up, so that way we're popping that element. So I know it's also a little bit confusing. When you're pushing it, you're actually subtracting. When you're popping it, you're adding it. So it's kind of unintuitive a little bit, but that's how x86 works. So now we want to figure out how to control our program. So we go back to our main function for a little bit. We notice we have this call auth. But wait a minute. What does call do? Isn't it just jumping from main into this auth function? Don't we have a jump instruction? Is x86 really that redundant? We have a call and we have a jump instruction that does the same thing. Think about it. We have a jump instruction to jump to different addresses, and we have a call instruction that does the same thing. Or does it? What else do we do for that? So actually, this call instruction does a little bit more stuff than just a jump. What it also does is it has a invisible push, and then the current instruction, instruction pointer, which is where we are in the code. So it's also written as RIP, or the instruction pointer IP. So why do we need to push our instruction pointer onto the stack?
So we got a function now where to go back to.
Okay, so we need to know where to return to after we finish calling auth. So here we have a call, and this call corresponds to this ret right here, this return, telling us to return to the parent function. Wait, did you have a question? Okay. I think it's okay. So this return function actually is an address. It pops it does another pop. It extracts that return address and then it returns. So that's kind of interesting because maybe we can override that return address with wherever we want to jump to. Maybe let's get shell, and then we can finally get the shell. So maybe let's do that. Let's just get a shell, and then we can exploit other stuff once we have shell. I'll show you why you might want to exploit such programs. So now let me write a simple program because it's a little bit confusing with this large program. So I'm just going to write a simple C program, and then let's just do main. So we have a main function, and let's say we have some function called funct, and then let's call funct. So it does nothing. Let's just have it return 5. Why not? Actually, let's return 42. Okay. So let's return 42, and maybe let's print that out. Why not? So here, what I have here is a very simple function, a funct that returns the value 42, and then we call a printf that does a %d, which prints out that number. So very simple. Let's see if it compiles with some warnings, because I didn't add the headers. Don't do this. You should add the headers, like include stuff. So if I run this, it prints out 42. Very nice. But let's see what it does under the hood. So here I have a GDB, which is a debugger. And you might think this looks a little bit different because I actually have something called GDB Peta, which allows me to see a little bit more colorful stuff. I'll show you why. So let's run it, start it up. So here we are in our main function. So here we have the push RVP, move RVP, RSP, and then as usual. And let's zoom out a little bit so that we can kind of figure out this. We can actually see the registers. So we have RVP, which points to some address. So this is the value of RVP. This is the value of RSP. We notice that here they're the same thing. Yeah, because our stack frame here in the main function is nothing. So, and we notice that on the top we have some stuff. But yeah, let's continue. So we step into it. I just type step I, which allows me to step instruction by instruction. Now we're in the funct class, or funct function. So we notice that now we have another entry here. So this is our stack right here. And it can show us what values we have in our stack. So here we have a 3.8, which is this thing right here. So F38, that's what our stack is at right now. And we see that we have it point to an address, or what's the stack value here at this address is some other address, which is actually a return value. So we return to hex 0x400520, which actually is back up here to this instruction. So we see that we have a call instruction that actually directly goes to the next instruction. That will actually, once you call ret, it'll actually jump to that instruction effectively. So now we call push RVP, which will actually push the value of RVP, which is this one, onto the stack. And then we move RVP into RSP, or the other way around. And then we return hex 2A, which is 42, and then we pop RVP. So we pop it, now we notice that that element is gone. and the RSP is moved up to 8, is incremented by 8. And then we return, we notice that it will return to this function. But maybe let's do something interesting. Let's return it to another address. So here, let me actually modify it in memory, because maybe it will always return there. But I will show you that is not the case. Even so, here let me set a value. So let me set. So this is the address of the value I want to set it to. So let me copy that, and then I want to set it to, let's say, hex leet. So if I run that, if I do that show out again, we notice now it points to the value leet instead of the return address. So if I actually step into that, step return, where do you think we're going to return to? We'll see. So here, now we see, oh, wait, we don't get anything. We see, oh, we do see invalid PC address, so program counter, and then we see leet. Oh, we returned to leet, but there's nothing there. So if we step through it, we realize we get a seg fault right here. So I guess that's GG. If I continue, it will actually say, we have a seg fault. Please help. And now we see that we are actually in that address, or our IP points to some leet value. And
that set thing you did?
Huh?
So you're setting an address to something?
So I'm setting an address, that memory of that address to a value. So if I scroll up again, here I have this address right here I want to set to. This address points to a block of memory, and then I want to set leet at that memory. I want to set leet. So that's where that came from. And then long tells me that I'm editing a 8-byte integer. So yeah. So now we can do this again. We can do this now with the other program, with this program. So this is kind of a little bit more tricky. So here I actually skipped out this instruction. We noticed that we're actually subtracting RSP by hex 30, which is allocating hex 30 bytes of stack space. So, and then we notice that hex 30 is also being passed to user input. So we notice that how many bytes do we have to overwrite to get to the return address? 48. But you're close, but there is something else we forgot. What else did we push onto the stack? Base pointer, yeah. So how many bytes is that? 8. So I have to add 8 more. So we actually have to override 56 bytes. So yeah, you gotta make sure. Another thing for buffer overflow, you gotta know where to over how many bytes to overflow, and what you're pushing on the stack. Because like this one, there could be more stuff you're pushing, and you have to account for those bytes as well. So here, I have a shell again. So I'm just gonna go do it easy. So now we have this. So I'm just gonna go run it. So I'm using Python to basically help me write that the shell code, or the input I want to send. So here I just have to write Python. So here I'm just doing Python commands. So I want to print out. Here, actually, I have a better idea. So screw the Python. Okay, so we're going to use echo. And then we need to do hexadecimal characters. So we're going to use the E option. This allows us to do this allows us to do hex escape codes. So we have 56 characters. Let's see, right? 56? Is that what it is? Okay, so I'm just going to go 1, 2, 3, 4, 5, 6, 7, 8. Oh, I skipped 4. So let's just do that. Very easy way. So that's 56 characters, right? And now we have to override that address. So if we override it right now with 8 A's, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so now we have this thing. Let's put it into a file. So I'm saving into a file called exp. And let's give that file to shell. So now we have a password. We have to wait again, which I really despise. Okay, so now we get a segmentation fault. That's good because now it's saying that we're trying to jump to a part of memory that doesn't exist. And that's correct because there's no memory such as AAAA. And in hex, it will be hex 41414141 41441. I can show you that. If I run GDB again. No, I was supposed to pipe exp. So now we're running it. And then GDB will tell me, hey, we have a seg fault. Right? And now we have this value, AAAA, on our stack. That's interesting because that's what we input right there. So let's just step into it. Okay, we don't get anything. It won't let us return. It won't let us jump to this address right here. Maybe let's change it to something else. So maybe let's do AAA and let's do zeros over here. Something like that, right? So if I run it again, so now we actually see invalid PC address 4141414141. So now we get a different message. That's because now we're returning, now we actually jump to that address. And then we're now in a part of memory that we don't have any code. So now, here comes the fun part. We have to figure out where we can jump to. But wait, I remember we also have a part of code that actually gives us a shell. Maybe we can get that. So let me go back to this shell. We see that at this line, we see a call to system. Maybe let's jump to there. Why not? So I'm gonna make sure we pass in the arguments. So let's jump over here. So I wanna know what the address is. So let's go to text view. So right click and you go to text view, it'll give you this thing, which is the text. It'll give you like all the lists of addresses and you just copy that thing. It's a little bit tiny, but you see what I'm selecting here? I'm selecting the instruction that will move command into EDI. If I copy that, now I need to figure out how do I send that. So how do I send that? How do I send this address over here?
Little Indian.
It's Little Indian. What's Little Indian?
First.
Okay. So we remember we're accessing a program that uses binary digits. So we have to actually convert this into bytes. So this one is 8 bytes. So we have this thing, and then we have to pad it with zeros. So 5 zeros. So wait, that's 1, 2, 3, 4, 5. Okay, something like that. That gives us 8 bytes right there. And then with echo dash E, remember I told you we need to use that. The reason why is now we can actually just do \x, and it'll give you that hexadecimal value. And I already realized that this is going to fail. Can anyone tell me why? Not the null terminated. That's not the issue. Actually, see, the issue is this hex 0A. What is hex 0A again?
Line feed.
Huh?
Line feed.
Line feed, yeah. So we realize that read input is actually going to stop right there and not going to read any more bytes. So what we have here is we got to make sure we jump to a valid address. So if I actually pipe into shell, and then we wait, it gives us a shell, but wait, it somehow works. Okay. Okay, so I guess it works. We can see that we have an @ symbol. Okay, I guess it gives you a shell anyways, but it actually doesn't jump to where we expect it to jump. So another way is we can actually choose a different address. So let's just choose this address right here. And I think that's where it jumped to. So again, we change this to hex 0 instead of hex A. And then we run shell. And now we say we get a shell, but immediately after that, we get a bus error. That's an interesting error. I guess it's writing exploitations. It's not that easy, but we do know that we got shell. And let's just run it in GDB to see if we actually did get that. So again, we run it. Oh, it runs. And then look at this. It says you get a shell, but then what happens after that? You get a new process, it runs dash. So it runs the shell, but then it exits immediately. Why do you think that happened? Huh?
It moves the next instruction.
It removed the next.
No, the program counter went to the next instruction.
Okay, not exactly. See, when we run bash or dash, when we run out of stuff to read, do we just exit? Does the shell just exit? So what we have here is we don't have any more input to feed it. So let me illustrate that. Let's say if I were to run, let's say at first I need to have a new line. So I can tell read input to stop reading more input. And let's write some of this, right? And then we run that program again, which is very annoying. And I'm kind of frustrated by it. Oh, we get something new. We get binsh1 DSAK not found. So it looks like that's just reading instructions from EXP. So we can also do this. So let's say we want to cat the flag. So I'm just writing a shell command right there at the end of everything else. At the end of our payload. And then we notice that we get a flag. So here, if we're running a CTF, this will actually give you a flag. And actually, I have something that's actually running. So here, I have a server that's running. So this one is my server. Or you can also change that name to the kitofarcrania.com. And when I SSH into that, so this is the command you would run if you're on Linux or on Mac. I think this will work on Mac. So now you have a password. The password is tag is cool. No caps, no spaces, no caps, nothing. It's just one line, just characters, lowercase letters. So we now have a shell, and we have a program that's very similar. So now we can run shell. We realize it's the same thing that we just worked on, except now it's colored differently. So if we paid attention, if we tried to cat the flag, it says permission denied. Okay, let's look at what the permissions are. So here we have an interesting S here. Let's see, we have an interesting S bit. So yeah, this is a little bit not assembly, if you noticed. But does anyone know what the S bit is? So the S bit actually lets you run as the whatever user or group. So this one lets you run as shell pawn. And then we see that only shell pawn can read the flag. So if you're not shell pawn, you can't read the flag. And then we notice that right now we are not shell pawn, we are just a regular user. Let's see if I can figure out. Oh yeah, ID. So right now we have our group is now shell. So we're not shell pawn. But if we run this, we can actually be able to get a shell and then cat the flag out or print the flag out, and you'll get a flag. So I kind of walked through all the steps, and on your own time, I would like you to kind of figure out this flag. Kind of run through this exploit again and try to get the flag. And I think that will be it for today.
So going back to when you're inputting into the buffer and you put the /n line feed and then you put a cat flag.
Yeah.
So /n is going to, you said, stop it from reading the buffer.
Yeah. It'll stop the read input from reading more inputs.
So where is that cat flag coming in?
That cat flag is actually being read by the shell program.
So it's being read in the terminal.
Yeah, it's read by the shell. The shell. Yeah. So that's where the cat flag comes in.
By the way, what is the password to this room?
Oh, this shell? It's tag is cool. So tag is cool. That's basically the password right there. It's also on the website. So if you want to go home and do it, you can access our website and the password is up there. So yeah, that is today's presentation. I hope you enjoyed it. Yeah. Come on. Come on, internet. Internet's UTD Wi-Fi is always bad. Why is it taking so long to do stuff? I don't know. We'll see. And we move RSP, which is a stack pointer. Anyways, let me finish the live stream. And by the way, for all of you here, I also live stream on the tag channel. It's also, I think it's somewhere on our website. Let's see if if I could figure out how am I going to end this live stream. I can't do this. Why is YouTube so difficult to work with? Okay.